Hello, this is Scott Dahman of PowerWorld Corporation. In this session, we'll talk a little bit about the power flow problem and how voltage control is done in PowerWorld Simulator. PowerWorld Simulator uses three nested loops to solve the power flow problem. The inner loop is what's traditionally called the power flow solution, which uses Newton's method or other nonlinear methods to get convergence of the nonlinear equations. The next loop is the voltage controller loop, which we'll talk a little bit in greater detail in this session. And then finally, the outer loop is the megawatt control loop, where interchanges between different control areas are balanced. The inner loop is where the power balance equations are solved for all buses in the system. For a system with n buses, the matrix equations that represent the relationship between current and voltage are shown here. This is basically a form of Ohm's law for an n-bus power system. In large-scale power systems, we usually model loads as having constant complex power, which gives rise to nonlinear equations for the power balance, in which the complex power is expressed as a product of the voltage and the current, and is relatively constant for all values of voltage. So substituting in the last equation, and then converting the matrices to 2 times the quantity n minus 1 real equations, we get an equation in the form shown here. And we need to solve for the x variable, which is also called the system state, which consists of all the voltage magnitudes and angles at every bus in the system. The n minus 1 comes about because of the slack bus, or the reference bus, for which the voltage and magnitude and angle are given, and then everything else in the system is solved relative to the voltage, magnitude, and angle that occurs at the slack bus. To elaborate more on the slack or the reference bus, exactly one bus in each electrical island is designated as a slack bus, which provides an angle and voltage reference. This bus must include a generator so that the slack reference angle and voltage can be maintained. That generator has a real and reactive output which is free to vary in order to meet the slack bus equation. Simulator will try to keep the real and reactive power within limits, but if it's not possible, then the generator will violate the limits. A well-conditioned case, of course, will have a slack bus generator that does maintain its physical limits. Other buses that contain generators are normally referred to as AVR generator buses, or automatic voltage regulation buses, or PV buses. The voltage magnitude is fixed or specified by a set point in the generator. The reactive output of the generator is free to vary in order to maintain that voltage set point. And most other buses in the system are PQ buses, or load buses, where the real and reactive power injections are fixed and specified. Solving this system of nonlinear equations requires an iterative technique. Several solution methods for nonlinear equations are discussed in the academic literature. Newton's method is a very common and popular one that Simulator uses. Simulator can also use a fast decoupled method, and a Gauss-Seidel method is also used in literature, but not in Simulator. Newton's method, as applied to power systems, consists of making an initial guess of the system state, or the voltages and magnitudes, at all of the buses except for the reference bus. And then there's an iteration counter depicted by K here. And this loop is basically repeated until the mismatches are 0. In other words, such that the guess for x satisfies all the equations in the system. The J matrix here represents the Jacobian, which is a matrix of partial differential equations that relate the real and reactive power to the voltage magnitude, and angles at the buses in the system. In Newton's method, if the guess for the system state, or the x vector, is wrong, that gives rise to a set of mismatch equations, or basically inconsistencies in the power system where the flows coming into a bus do not all sum to 0. This can be illustrated in the 7-bus sample case called B7 flat in Power World Simulator. If we first make sure that the case is solved, and then we make a change such as opening the line between bus 2 and bus 5, the system state that was solved with that line in service is no longer valid. Right now we'll have a mismatch at bus 2 and bus 5 because of the flow between the two that we've taken away in opening the line. If we open the Model Explorer, we can take a look at the mismatches in the system. In the Explore tab, inside the Network group, click on the mismatches. These are sorted in descending order, and we can see that at bus 2 and bus 5 we have a mismatch equal to the flow that was on the line before we opened it. The mismatch display also shows what type of bus each bus in the system is: PV bus, PQ bus, or island slack. If we open the message log and solve the power flow again, we can see the process by which Simulator uses Newton's method to drive the mismatch to 0. And in the solved case, we can see that these mismatches are all 0. And if I scroll up in the message log, I can see the process where initially I have a mismatch at bus 2 of 78 megawatts of real power and 0.641 megavars. With each iteration of the inner loop, this gets driven closer to 0. Then Simulator goes into voltage control loop iterations and also megawatt control loop iterations to balance all of the constraints in the power system for voltage control and for megawatt interchange. When the case is finally solved, all of the loops are balanced, and Simulator reports a successful power flow solution. The slide here describes this example. Also note that the voltage magnitude at generator buses remains fixed. The Simulator options allow you to modify some of the settings that govern the power flow solution. In Simulator, from the Tools ribbon, or from the Case Information ribbon, or from the Quick Access Toolbar, if you have the button there, you can click Simulator Options to bring up this dialog. For the inner power flow loop, you can specify the MVA convergence tolerance. This number must be greater than 0, and this determines how close is close enough during the process of trying to zero out the mismatches. You can specify a maximum number of iterations as well. If Power World Simulator cannot solve the power flow before the maximum number of iterations, it will report that it failed to do so in the message log. You can also check this box to do just one iteration, and if you do that, then every time you hit the single solution button, it'll just proceed one iteration of the inner power flow loop at a time. And that way you can see what's happening in the inner power flow loop and perhaps diagnose any problems in the solution. For the megawatt control loop, or the outer loop, you have the option of disabling automatic generation control. And this will basically keep generators from moving according to their AGC settings, and it'll also disable the enforcement of area-to-area megawatt interchange constraints. You can also globally enable or disable the enforcement of generator megawatt control limits. So I'll go ahead and check that. For the middle loop, or the voltage control loop, we have the ability to disable the operation of the generator VAR limit checking, or the switch shunt control, or load tap changing transformer control, or phase shifter control. Normally you do not want to disable any of these, but if there's a problem with getting the power flow solution to solve in a large case, sometimes it's helpful to disable these and then solve the power flow and then go back one at a time and re-enable them. If a transformer that is controlling a voltage or a flow, in the case of a phase shifting transformer, is out of range, in other words, the quantity that it's trying to control is not within the minimum and maximum range that's specified for the device, simulator will normally try to move all of the transformers back into range together, and that's referred to as the coordinated sensitivities. You can also choose to use self-sensitivities only, in which case each transformer will move in the direction that tries to get its own quantity back into range. Normally the coordinated sensitivities are more effective. Simulator also has an internal algorithm for preventing controller oscillations. So if you have a situation where one load tap changing transformer moves in one direction to try to improve its voltage, and that causes problems with another controller and forces another controller to move in another direction, which then in turn forces the first controller to move back, simulator will detect that situation and basically turn one of the controllers off and allow just the other one to move. Normally it's very helpful to allow simulator to use this internal algorithm, but if you do want to disable it, you can. And then you can also specify the minimum number of iterations that simulator, or rather the maximum number of iterations that simulator will go through in trying to resolve all of the constraints in the middle voltage control loop. And the slides also describe each one of those options on the Common Options tab. Underneath the Power Flow Solution options, the next sub-tab to the right is called Advanced Options. The checkbox up at the top allows simulator to dynamically add or remove slack buses if an island is created by taking lines out of service. If the box is not checked, then if part of the system is severed through opening transmission lines, then the part of the system that does not include an island slack bus already will basically go dark. So for example, if I close this dialog, and in my case I open the lines between bus 5 and 7 and bus 2 and 6, I will create a separate island which includes buses 1 through 5 in one island and buses 6 through 7 in the other. Now bus 7 initially has the slack bus for the entire system. If I solve the power flow right now, then buses 6 and 7 and their island will continue to operate, but everything in the other island, which includes bus 1 through 5, will go to 0 per unit voltage with no output from any load or generator. If I go back into the solution options and onto the Advanced Option tab and check this box to dynamically add or remove slack buses, and then click OK and resolve the power flow, then I'll see that simulator has automatically assigned bus 2 as being the slack bus. It will take the largest generator in the new island and assign its bus as the slack bus. Also, if I go to my Model Explorer Underneath Aggregations, I can open a case information display for islands. This will show that I have 2 islands in my case, and it will identify the slack bus in each one. Summary information such as generation and load is also shown for each island. The slides describe the other options which are available on the Advanced Options tab. The button for Post Power Flow Solution Actions allows you to define a list of actions which include after every power flow solution. So an example might be to specify that loads drop automatically if the voltage at their terminal bus drops too low. Most of the remaining options on the Advanced Options tab allow you to disable certain features of the Power World Simulator solution algorithm. And normally you don't want to disable these because they work well for a purpose. But if you're having some issues with getting a solution to solve and you want to diagnose things a little bit further, then you may want to experiment with some of the options on the Advanced tab. There's an option for disabling the optimal power flow multiplier, which is a mathematic algorithm which allows simulator to take a step between each Newton iteration to try to drive the mismatches down to 0 as fast as possible. It also prevents the equations from diverging. You can initialize the solution from a flat start, which basically tells every bus and every bus in the power system to start with a voltage magnitude of 1 per unit and an angle equal to the slack bus angle. Normally, if you do this on a large scale case, it will result in a failure to converge. So it's not recommended. You can also specify the minimum per unit voltage for constant power and constant current loads. And specifying a non-zero value here will generally help provide stability to the solution, in that if the terminal bus voltage gets too low, then the effective power will actually back off a little bit. And that helps simulator solve if the values are above 0 by some amount. But you might want to disable these features if you're doing a voltage study in which you want to experiment and analyze conditions under which bus voltages get extremely low. In that case, you might want to just set the values to 0. If we go back into the Simulator Options menu, we can see where these features are. And again, on the Advanced Options tab, we can see here that the minimum per unit voltage for constant power and constant current loads are set to 0.7 and 0.5 respectively. So what that means is that there is a function which has a continuous first derivative that basically causes the effective power at the bus to start to drop off from the nominally specified amount if the voltage at that bus gets below this value. So essentially, to disable this function, you would set these values to 0. Other advanced options are described on the next 2 slides. On the Options ribbon, there is a Solution drop-down box which provides access to a lot of the same settings that you can get in the dialog that we've just looked at. So if I select my Options ribbon and then the Solution drop-down, I can see a lot of the same settings that were in that dialog. It just provides a quicker way to get access to them if there's just 1 or 2 small changes that you need to make. Back inside the Simulator Options dialog, the next sub-tab to the right is called Island-Based AGC. And the Island-Based AGC feature allows you to override the area and super area dispatches such that every electrical island acts as one big super area. And if you want to use that, you would select one of these three other options besides the first one, which is disable. So for example, you can use a participation factor of individual generators. And that determines how the generators within each electrical island respond to changes in load or losses or generation. You might use a feature like this to analyze what would happen in the event of an outage immediately after the outage, before different control areas would be able to respond by trying to drive their ACE to 0. So if a generator is lost, a large generator in the system, in the immediate seconds that follow, there's probably going to be some sort of governor power flow that dictates how that power is made up, rather than each individual control area being able to respond accordingly in order to keep each control area's ACE as close to 0 as possible. There's going to be a transition time or a transient time in there in which the ACEs will be non-zero. So you can use the island-based AGC feature to analyze situations like that. But if you don't want to use it, then you can just choose this first option, which disables it and allows the super areas and the control areas to dispatch megawatts according to how each one of those are set up. The third option then allows you to specify for each control area a participation factor for which that control area responds in making up power in the entire electrical island. And then the final option allows you to use injection groups to dispatch when a change is made. And in order to use that, you have to have an injection group defined first. If at least one injection group is defined, then you can specify how those injection groups behave in this section of the dialog here. The next tab to the right is the DC Options tab. And this allows you to use the DC method for solving the power flow, the optimal power flow, and the security constrained optimal power flow. The DC approximation basically ignores voltage, megavars, or reactive power, and losses. It's going to assume that every bus in the system operates at 1 per unit voltage, and there's no reactive power output from any of the generators. The method is called the DC approximation because the resulting power flow equations represent the equations for a DC circuit. It does not, however, assume that only the DC lines in the power system are used. The advantages of using the DC approximation are primarily in speed, and also in the fact that the DC solution, or the DC approximation, will almost always result in a converged solution. So if you're changing load or making radical changes to the system, taking lines out of service, it solves much faster, and there aren't any of the pitfalls that can sometimes occur with trying to get the voltage control loop to converge. However, some of the accuracy and some of the modeling is lost, and the rest of this section, the other sections in this dialog, allow you to make some approximations that attempt to make up for some of the detail that's lost. The DC approximation must ignore either the real part of the impedance, which is the resistance, or the little r, or the real part of the admittance, which is the conductance, or the little g. Strictly speaking, ignoring the conductance is a little bit more accurate, but sometimes resistance is ignored in some DC models. So Simulator gives you the option of choosing either one. If I go ahead and select the DC approximation, I'll then have access to some of these other options. You can compensate for the losses, which are not explicitly modeled in the DC approximation, by adjusting the load, or basically building the losses for each control area or each zone or other part of the system into the loads. And to do that, I can click on the DC loss setup button. And here is where I set the DC loss multiplier. I can add in multipliers for each bus if I wish, or I can automatically set them for each area or zone by choosing the area or the zone tab and then clicking set. And what it's going to do then is apply the DC loss multiplier that's calculated for the area or for the zone to each bus in the area or zone. And it's important to note that the DC loss multiplier actually acts on buses. So in the end, when you close this dialog, it's the value in the bus that determines how simulator approximates for the loads. But you can use the area tab and the zone tab if you wish to set multipliers by area and by zone. You can also set every bus in the case equal to the same DC loss multiplier. Simulator also allows you to automatically have the line ratings, the line limits, derated in order to adjust for the fact that there aren't any reactive power flowing on the lines. And the default option is just to ignore the reactive flows. So the limits on the line will basically then apply only to the megawatt flow. But you can also have Simulator automatically derate the lines, and in order to do that, it's going to assume that the voltages at each terminal bus for the transmission line remain constant, and then it's going to assume a limit which is based on constant voltages. And then finally, if you want to incorporate marginal losses into the dispatch sensitivities for the optimal power flow or the economic dispatch algorithm, then you can check this box here, and it will allow Simulator to incorporate the loss sensitivities that are user specified into the OPF and economic dispatch algorithms. The loss sensitivity function itself is set on the next tab, or the general tab. But if you're using the DC method, it cannot be updated, so it can only be used if the loss sensitivity function is set to user specified on the general tab. The slides also summarize some of the options available on the DC Options tab. It's important to note that for a large-scale system, if you convert it to the DC approximation, it's very unlikely that you'll be able to get the case to resolve in the AC system or without the DC approximation in the future. So if you wish to use the DC approximation, it's probably a good idea to first save a copy of your case that has the AC solution in it, the full AC solution in it, before you switch to the DC approximation. Then perhaps you can maintain two copies of your case, one with the AC solution and one with the DC. And the following slides discuss the other options in detail. The General tab on the Power Flow Solution options allows specification of the bus loss sensitivity function, which we briefly discussed. User specified means that the user can enter the losses for each bus, and this is useful if you're using a DC solution. The first option is do not calculate bus loss sensitivities, in which case each time you solve the power flow solution it will not update the bus loss sensitivities. For each of the remaining options, Simulator will then automatically calculate bus loss sensitivities after each power flow solution, and you can specify how those sensitivities are related. Each electrical island will basically calculate the bus loss sensitivity for an injection at each bus, and it will determine how the losses change within the electric island that that bus belongs to. The injection is assumed to be taken out at the island slack bus. You can also have it compute the loss sensitivity just for the area that each bus belongs, or each area or super area that the bus belongs to, or just the area selected on the loss sensitivity form. And more information about loss sensitivities can also be accessed under the Tools menu, and that'll be discussed in greater detail in a different topic. If you have interfaces which include contingent elements, so line outage contingent elements or line insertion or line closure contingent elements, then you can specify whether or not those interfaces should be, that the flows on those interfaces should be calculated. The default is to not calculate them, and that is just to save some time in the solution. But if you do have contingent interface elements, then you can choose to monitor and enforce them just during the power flow solution in the OPF, but not contingency analysis or security constrained OPF, or to monitor and enforce them always, including the contingency analysis and the security constrained OPF. Contingent interface elements are discussed a little bit more in the topic on system aggregations. And finally, the Storage tab has a couple of options for saving some system memory. You can choose to disable the feature which allows you to restore the last solution, or you can also disable the feature which allows you to restore the state before a failed solution attempt. And with these buttons dechecked, then you have the option, if a solution fails, to go in and restore either the last successful solution or the state of the system immediately before you attempted to solve the power flow. These features are both generally useful, but they also take up some system memory. You can access the restored states from the Tools ribbon. So if I close this and go to the Tools ribbon, there's a drop-down for Restore. And if I choose that, I can restore either the last successful solution or the state before a failed solution attempt. And of course, these options are only available if you allow them in that Storage tab. And the slides here summarize the options on the General tab and the Storage tab. The General tab also allows you to change the MVA per unit base of the system. And normally that's chosen as 100 MVA, but you can change it if you wish. And of course, the value of the complex power or MVA base of the system will determine how impedances are expressed in per unit, how the per unit values are derived from the underlying physical quantities. The next few slides describe in greater detail the electrical islands that can occur in the system. Some power system models include just a single interconnected system operating in AC synchronism. However, some models that we get, particularly in the Eastern Interconnect cases that are modeled in North America, we can see multiple islands that are connected only through DC connections. So the Quebec region, for example, is connected to the rest of the eastern part of North America only through DC lines. And also, some parts of ERCOT and some parts of the Western Interconnect may be modeled in an Eastern Interconnect case, connected only through DC transmission lines. So subsystems that operate either independently or only through DC connections are called islands. Each island must have its own slack bus. And we did the example earlier where we allowed multiple islands from the Advanced Options tab. These slides talk about that example that we ran through earlier. So on the Advanced Options, you can check the box that dynamically allows Simulator to add and remove slack buses as the topology is changed. And you can sever the 7-bus system into 2 separate islands. And here's a one-line diagram of what that system would look like. In this case, with bus 2 to the line between bus 2 and 5 in service. And with multiple islands, the 2 systems are modeled independently of one another. And The generator at bus 2 becomes the new slack generator for the top island. And the island's record display inside the Model Explorer shows the 2 islands. Inside the Power World Simulator Options dialog, in addition to the PowerFlow Solution tabs, which we just looked at, there are other pages that deal with very specific things, such as the message log, file management, the environment inside Simulator, case information displays. And much of these are described in detail on the slides. This slide describes the message log page, and you can customize which messages occur inside the message log, and also the colors in which the text appear for each type of message. The environment page allows you to specify several options which are saved to the system registry, so that each time you open Power World Simulator, certain characteristics are maintained. Among other options on this page, you can specify how much memory is allocated to being able to undo things that actions that you perform on one-line diagrams. And the larger memory buffer that you allocate for that, the more actions in succession that you can undo, but also the more memory that is required by that feature. You can also specify the list of recently used files that appear under the application icon for you to be able to quickly open. You can adjust the number that are displayed there. The one-line page allows you to specify some characteristics of how things appear on the one-line diagram. You can choose, for example, to only animate the existing PowerFlow solution rather than having Simulator resolve repeatedly in succession when you animate. Again, animating is when you press the play arrow on the Tools ribbon. You can also specify that a particular one-line is always opened whenever any PowerFlow case is opened. And other related options, such as whether or not one-lines are automatically saved when you save the case or the PWB file. I recall the one line is saved separately in the PWD for display. The File Manage page allows you to specify that a particular auxiliary file automatically load whenever the case is opened. Or you can also specify that a particular auxiliary file is loaded anytime any case is opened. There's also a section for specifying an autosave in which the PWB gets saved into a temporary autosave file on a specified interval. You can also automatically archive the PWB files each time you save. So when you click the Save button, it will save the last version in an automatically archived file. And you can choose how many files to archive and then also how to name them so that you can tell them apart. And then there's also a tab for special options associated with the GE EPC and the PTI RAW file. The Case Information Displays category allows you to change the appearance of text that occurs in the case information displays. These are the text-based displays that occur inside the Model Explorer. The Limits tab has some specific options for generator limits and also for transmission line limits. They can be automatically opened, and the checkbox to enforce generator limits is basically the same checkbox that occurs also on the PowerFlow Solution General Options tab. Next, we'll talk about using generators, switch shunts, and load tap changing transformers to control voltages in the power system. Generator Automatic Voltage Regulation, or AVR, allows you to specify a voltage magnitude for a regulated bus. A generator can regulate the bus at its terminals, or it can also remotely regulate another bus, for example a high voltage bus on the other side of a step-up transformer. A bus can also be regulated just by a single generator or by multiple generators that are sharing responsibility for regulating that bus. In Simulator, we can look at the generator AVR options by right-clicking on the generator symbol either in the one-line diagram or in the Model Explorer, and then bringing up the dialog for that generator. So back in Simulator, I'll switch to my one-line diagram, and I can right-click on a generator and open its information dialog. The first tab here on the left is the Power and Voltage Control tab, and the voltage control is on the bottom section of this dialog here. Here is shown the generator's present megavar output, as well as its minimum and maximum limits to megavars. There's a checkbox which indicates whether or not this unit is available for AVR. If I clear that box, then the megavar output for that unit will remain fixed, and it will not be allowed to vary in order to regulate voltage. Here I can see which bus is being regulated. In this case, this bus is regulating the voltage at its terminal, and the desired voltage that it's trying to regulate to is 1.05 per unit, and then this box shows that the bus is actually at 1.05 per unit. As long as the megavar output of the unit is within its range, its min and max range, then it should be able to control its voltage. There's also a remote regulation percentage, and if a bus is regulating a different bus besides its terminal bus, say a high voltage bus on the other side of a step-up transformer, and if there are more than one unit that are regulating the same bus, then you can specify a remote regulation percentage, which is basically a participation factor that says how much of the total regulation responsibility for regulating that remote bus is going to be taken on by this particular generator. So for example, if you have 4 generators that are each regulating a high voltage bus, you might set each one to equal 25%, or you can change that as you see fit. So here I might adjust the minimum and maximum megavars to maybe some more realistic values. Right now it's minus 9900 to 9900. Maybe I'll change it to minus 400 up to 400. Now, in addition to specifying just one number for the limits, for the minimum limit and the maximum limit, you also have the option of specifying a capability curve, which allows greater detail in modeling and also more realistic detail in modeling the megavar capability of a unit. If I choose that, then I can specify different megawatt breakpoints, and at each megawatt breakpoint I can have a different minimum and maximum megavar. And by default, it's going to add the minimum megawatt capability of the unit, which in this case is 100 megawatts, and the maximum capability of the unit. So perhaps at 100 megawatts, I have the capability of running from say minus 400 megavars to plus 400 megavars. And I can also insert some intermediate points here if I wish. So I'll insert a new point, and let's say at 200 megawatts of output I have the ability to generate 300 megavars, both positive and negative. So I can enter those. And this allows you to put in a more realistic kind of bell-shaped curve for the megavar capability. And for most units, the more megawatts they're producing, the less capability that they have to produce megavars. So maybe at the full output, I can only generate, say, plus or minus 50. So I can enter that. Now once that's complete, I can click OK, and then I can right-click on a unit too and say that I want to show the reactive power capability curve. And this will show the present operating point, which right now we're only generating again about 8 megavars. But this shows, the black lines show the region of capability, and here's where we're operating. You can also view a generator's reactive power parameters from the Model Explorer. And if I click on generators, I can add fields to the display if they're not already there for the reactive power capability. So if I click on the fields and then the megavar output, I can drag some of these fields on, such as whether or not the unit is AVR, the present megavar output, and the minimum and maximum. And, for example, whether the capability curve is being used. So I can see for this unit that it is using the capability curve, and the minimum and maximum are grayed out. And there are also fields for regulation under the regulated bus group here. So you can bring those fields on as well. Now the capability curve itself is really best specified within the dialog. So if you need to adjust the capability curve, you can do that for each unit by showing the dialog and adjusting the values down here. It's important to note that the reactive capability curves that can be specified in Simulator are not part of the raw file format or the EPC file format. So if you make adjustments to the reactive capability curve and you want to save those and use them with other cases, you'll have to use the auxiliary file format or some other means of storing that data so that you can bring it in later. And the auxiliary file format is particularly well suited for that. So if I want to save this information off, of course I can right click and then save as, and I can choose the auxiliary file, only the selected records if I wish, or all of the records on the display. And if I do that, of course I can give it a name. I can call it generators, and then click save. And then it'll ask me if I want to save some of this subdata, such as the bid curve subdata. I can say no for that one, but if I do want to save the reactive capability curve data that I just created, then I could say yes to this. And that'll save those breakpoints that I stored for the reactive capability curve as subdata for that generator record. And then I could load it into a different case later if I wish. And the slides on generator AVR summarize some of the example that we just went through. And there's a slide here which describes in detail the remote regulation feature. And if you have multiple generators that are regulating the same bus, they will share the requirement for regulating according to the remote regulation percentage. So a little bit of clarification too, that generators that are at the same bus that are not regulating remotely will coordinate their VAR outputs so that they're within the same relative point within their VAR range, or between their min and max. They're at the same relative point. And here is described how you can define the reactive capability curve, which we did in the example. And here's a graph of the reactive capability curve, similar to the one that we created in the example. And a note about saving the reactive capability curve in the auxiliary file, or the text file format for Simulator. Next, we'll talk about using switched shunts, or capacitors, to control voltage. The switched shunts can be used to control voltage at the regulated bus, or to control the megavar output from a generator. Switched shunts can be controlled in discrete blocks, which kind of mimics the behavior of capacitor banks, or also on continuous mode, where it has a minimum and a maximum, and it can operate anywhere within that range. Automatic switch shunt control can be disabled in 3 places. Globally on the simulator options dialog, which we looked at, also for an individual area on the area records display, or for individual devices. In order for a device to be enabled, all 3 flags that correspond to that device must be enabled. To illustrate this in simulator, we're going to open the sample case B5R. And I will choose not to save the existing case. Here we have a switch shunt device attached to bus 3. And if I open my Model Explorer, I can look at area records and scrolling over to the right, I can see that the switch shunt control is enabled for both areas in this case. So I could toggle this and disable it for one or both areas, and then also at the individual device level. And I can open those under Network and then Switched Shunts. So here I can disable its control by placing it on Fixed Control, or by changing its status to Open. I can view or change the control characteristics of this unit by right-clicking on it and then bringing up its dialog. First of all, I'll place it in service by changing its status from Open to Closed. And then the control mode initially is set to Fixed, which means that whatever nominal megavar is being shown right here is what's being produced by the device. I can switch it to discrete control, and then if I do that, I have to go here to the right and change its control regulation settings. For discrete or continuous control, I have to have a high value that's strictly greater than the low value. So let's specify a high value of 1 per unit and a low value of 0.99 per unit. And the target value is specified as 1. What that means is that if the voltage that it's trying to regulate is outside of the high and low range, it will switch itself in order to try to bring the voltage to the target value. If it achieves a state where the voltage is between the high value and the low value, then it will stop moving. So here it is trying to regulate bus 3, and I can't change that right now because I'm in run mode, but if I were in edit mode, I could change the regulated bus voltage. And the section at the bottom shows the discrete blocks which comprise the switch shunt. So what this shows is that I've got 3 blocks of -10 megavars per step. So I have some inductive capacity here, which can be expressed in three steps or 3 blocks of -10. I also have 4 blocks of +20, and the device simulator can switch in or out basically any one of these blocks, so you can get any linear combination of the number of steps times the megavar per steps when you're in discrete mode. If you're in continuous mode, then simulator will allow it to produce a nominal megavar that is anywhere between the absolute minimum and the absolute maximum that could be achieved from those blocks. So in this case, the limits for the discrete, or for the continuous control, would be -30 megavars all the way up to +80 megavars. I have here also some checkboxes which show that the area that this switch shunt belongs to has its control enabled, and that the case globally has the switch shunt control enabled. And these are the options that we looked at earlier. For convenience, they can be toggled here as well. So if I close this dialog by clicking OK, and then switch back to my one-line diagram, and then from the Tools ribbon, click the Single Solution, I can see that the capacitor, the switch shunt at bus 3, switched on, and it placed 79 megavars in service. Now this is the actual megavars that it's producing. The nominal megavars are the 80 megavars, which are derived from the 4 blocks of 20 that were specified. The reason why the 79 is a little bit lower is because the actual megavar is dependent on 1 over the square of the terminal voltage. So because the terminal voltage is below 1, the actual megavar is below the nominal. And if I right click on the device to bring it back up, I can see that the nominal megavars are 80 and the actual is 79. I can see that the regulated value is in the range between 0.99 and 1. I can also see here too the sensitivity of the voltage to the megavar output. So what this is saying is that 1 more megavar at that bus will raise the voltage by this amount. In this example, I can also animate my power flow on the Tools ribbon by clicking the play button. And then I can experiment by varying the real and reactive power at this bus and seeing how the voltage changes and how the switched shunt reacts. So for example, I could reduce the megawatts and the voltage will creep up a little bit. I can get it to change even faster if I alter the reactive power at the bus. So if I start to decrease that, then the voltage will start to rise, and if it gets too high, we can see that the switched shunt reacts by taking one of the blocks out. So at a reactive power load of 35 megavars and 90 megawatts of real power load, the switch shunt then drops one of the blocks, and it's still within range. It's between 0.99 and 1, but it doesn't need as many megavars in the switch shunt. So if I continue to decrease that, I can see the voltage starts to come back up a little bit, and if it gets too high, then the capacitor will back off 1 more block. And if I change this to where I'm actually producing megavars at my load, I'll eventually get to a point where my switched shunt has to turn into an inductor, and the symbol changes to on the one-line diagram. The following slides contain some more detail about the example that we just went through. This slide describes how the switch shunt behaves if it's used to control a generator's megavar output instead of voltage at a regulated bus. In Simulator, if I switch to edit mode and then right click on this device to bring up its information dialog, and now I could choose, instead of regulating terminal voltage, to regulate generator megavars. In this case, the bus that I specify is a bus that's being regulated by 1 or more generators. And then the high value, low value, and target value that I specify now become megavars, and it's the sum of the megavar output for all generators that are regulating the bus that's specified here. And this slide shows a little bit more detail from our example. Next, we'll talk about how transformers can be used with tap controls in order to regulate voltage. Transformers can also be used to regulate the real power that flows through them when they're in phase shifting mode. Like with the switch shunts, the automatic control for transformers can be disabled in 3 places: globally on the simulator options dialog, for an entire area on the area records display, or individually for a device on the transmission line transformer dialog. And again, all 3 of these must be set to enable in order for that device to work. So back in our B5R case, we can right-click on this transformer between bus 4 and bus 5 and bring up its line information dialog. The tab entitled Transformer Control has the parameters that we're going to look at right now. So first of all, it tells you what the off nominal turns ratio is, and then also its present phase shift. It has automatic control enabled, as indicated by this checkbox right here, and I can go in to this button right here to bring up another dialog to adjust the automatic control options. So here it says that the control type is AVR. I can also choose to regulate the reactive power, and that can be used to regulate the reactive power that flows through the device, or you can use it as a phase shift control, which will regulate the real power that flows through the device. So with AVR control, I can specify a regulated bus, which is bus 5, and I'm in edit mode right now, so it's not showing the present voltage or the voltage error. But I can specify a minimum and a maximum voltage, and then whether or not the target is the middle of the range or the max or the min. Max or min being determined by which direction you're coming from. So if the voltage is initially below the minimum and you select this option, then the target voltage becomes the minimum voltage. If it's too high, then the target voltage becomes the maximum voltage. And these options are in here basically to be able to replicate the behavior of other power flow software, such as PSSE or PSLF. You can also specify the present tap ratio, which is the off nominal turns ratio, and then the minimum and the maximum tap ratio. These are the physical capabilities of the unit, as well as the tap step size. This is the discrete increment in which the tap ratio can be adjusted from its minimum to its maximum. I'm going to change the maximum regulation range to just 1 per unit voltage, and then click OK to close the dialog, and then OK again to get back to the case. And I'll switch to run mode and then solve the power flow. Presently, my regulated bus at bus 5 is within the limit specified by the load tap changing transformer. It's at 0.997 per unit volt, and the graphic next to the transformer shows that the tap setting is 3 taps to the low side. If I go ahead and play the animation like we did with the previous example, I can adjust the load at bus 5 and see how that affects the voltage at bus 5 and then the response from the load tap changing transformer. So as I start to increase the load, the voltage starts to drop. And if it gets outside of its range, then the tap changing transformer responds accordingly. And then the slides illustrate the example that we just went through. The remaining slides provide a detailed overview of PowerWorld Simulator's power flow algorithm and the actions that occur inside the 3 nested loops. They are provided for reference, and you can download the slides if you wish to review them. This concludes this session on reactive power and voltage control. If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.